Okay, let's take a look at part 3 of lab 9, the logarithmic amplifier. So we have once again, we have the input coming into the inverting input of the op amp, and so then the non-inverting input is grounded. So because this non-inverting input is grounded, the inverting input is known as a virtual ground. Okay, so basically negative feedback will keep this point at ground so that it matches the non-inverting input. So, and then you know that the inputs draw negligible current. So whatever current flows in through this resistor, I called that I, will continue to flow through one of these diodes. So if I is to the right, then it will flow through the lower diode here. And if you change the sign so that I is to the left, then it will instead flow through the upper diode. So the reason why we put two diodes, you really only need one diode if you know the sign of the signal you'll be looking at. But we put two diodes here in opposite directions so that if the current goes to the right, you can flow through the bottom diode. If the current goes to the left, it can flow through the top diode. That way we can handle a signal of either polarity. So then we can, okay, so the question is, so if this current flows through here, what is V out? So remember that for a diode, the current is an exponential function of the voltage. Current through the diode is an exponential function of the voltage across the diode. In particular, you have this quantity called I saturation. I usually just call it I naught, but I sat, e to the qv over kt. This q is the charge on an electron, or actually the charge on a proton. But I'm writing q instead of e because it's in an exponential. So e to the charge on a proton times voltage over kt. Sometimes there's a small factor, kind of 1 or 2 out in front of this q, the so-called ideality factor. And then there's the -1. The -1 is so that if v equals 0, because you know the exponential of 0 is 1, so if v equals 0, you get 0 current. But by the time the current becomes non-negligible, this -1 doesn't matter. So we can say I naught e to the qv over kt. Then you can turn that upside down and solve for the voltage across the diode as a function of the current through the diode. And we get that the voltage across the diode is kt over q, okay, where again this q is the charge on a proton, times the logarithm of the diode current divided by this saturation current. So now, if that's the diode drop, that's basically the left end minus the right end of this diode that we drew on the bottom. So if this left end is at 0, then this right end is at a negative voltage. So that puts V out at a negative voltage. So V out then is minus kt over q times the log of V in over I sat R, because the current through the diode is just this input voltage divided by R. You see, the virtual ground makes things so easy because this is 0, so this current is just V in minus 0, which is V in, and then divided by R. Okay, so what that gives us, all of this junk, normally you don't remember it. What you really remember is that the output is proportional to the log of the input. And we can be a little careful with the signs. So if the input is positive, then the output should be negative, and if the input is negative, then the output should be positive. So we can say V out is proportional to some constant of proportionality that we won't worry about. So it's proportional to minus the logarithm of, let's say, the absolute value of V in, and then we can multiply by the sign of V in. Okay, and then we have, so then what happened, right? Okay, so if the output were here's, let's say, V out, here, let's say, is V in. So if it were proportional, if the output were proportional to V in, you'd have a nice straight line. Instead, you have the output proportional to the logarithm of V in, So the logarithm function, I'm kind of, I have to be a little careful, but I guess, see, its slope becomes small here, and then its slope becomes very big here. Yeah, so you see, as V in gets big, then V out will appear proportionally smaller. It'll increase at a smaller and smaller rate. But as V in becomes small, then you'll see that V out is kind of exaggerated. So let's see what. Oh, great. Then I think. Let me see. Oh, that's not it. Right. So we'll actually get something that kind of looks like it kind of looks like this. It kind of looks like this. Yeah. Sort of looks like the waveform display. So we'll look more closely at that waveform display in a moment. But basically, you can see, well, actually, let me just put it off for a minute. We'll look at it more closely in a minute. But you can see at one end, you see, so when the magnitude of V in gets big, then the output gets flattened, kind of squished. And then when the magnitude of V in is small, then the output is kind of exaggerated. It has an exaggerated slope. So on one end of our triangle wave, we have this kind of exaggerated slope, and on the other end of our triangle wave, we have this flattened out slope. And it looks to me kind of like a gambrel roof. I'll show you a picture of a gambrel roof in a minute. Yeah, so there's what a gambrel roof looks like. And so I think, you can kind of see a resemblance between the yellow curve on the oscilloscope and the gambrel roof in the photo, but I digress. So let me also remind you of what's connected where. So we have pin 6 here is the op-amp output, so that's up here. We have pin 2 is the inverting input. We have pin 3 is the non-inverting input. Pin 4 is down here to minus 9 volts on the EE board, would be minus 15 with our classroom power supplies. And then pin 7 up here goes to plus 9 volts on the EE board. So again, going around the op-amp, pin 1 is not connected, so 2 is inverting input, 3 is non-inverting input, 4 is negative power, 5 is not connected, 6 is our output, 7 is our positive power, 8 is not connected. And so we should be accustomed to always seeing some kind of negative feedback connected from the op-amp output back to pin 2. So pin 6 back to pin 2, you should kind of get used to seeing that for some kind of negative feedback. And then most circuits we build will have pin 3 grounded, but not all of them. Okay, so I kind of wrote the pin numbers here just to remind you of that. So here is what the circuit looks like on the breadboard. So here is our op-amp, and it's a little hard to see, but pin 1 on the bottom left is not connected. Pin 2 next to it that's the inverting input, so that's where most of the action is. So we see the 1K resistor coming from the input signal to this non-inverting, to this inverting, from our input signal, we'll talk about that in a minute, over to the inverting input of the op-amp. And then you have our 2 diodes, and they're both a little hard to see where they're connected, but they're both connected from pin 6 back to pin 2. So they're both from the output back to the inverting input. And there's a little stripe on the diode package here. Let me see. So when you look at the diode, you see this long wire, and then there's a cylinder, and then there's another long wire, and there's always a stripe somewhere. And so that little stripe corresponds to the negative end when it's conducting of the diode. So the little stripe on the diode package, the little stripe on the diode package here corresponds to this line at after the triangle. So the current the direction of allowed current flow is toward the stripe, just like it's toward that little, it's in the direction of the little arrow on the diode itself. Okay, so in that case, we had to connect one of them with the stripe pointing toward pin 2 and one of them with the stripe pointing back toward pin 6. So you have to make sure you put the two in opposite directions. And then this black wire is connecting pin 3, the non-inverting input, down to ground. Pin 4 is not connected. Pin 5 is not connected. We already talked about pin 6. The other thing going into pin 6 here is scope channel 1, the yellow scope channel. And then pin 7 is going up to positive power, plus 9 volts. So again, I like to use this red bar up here for plus 9 volts. So you can see that I'm using a little, now you like to use red wires for power generally. And then down here I'm using this red bar on the bottom for minus 9 volts. And again, I'm using a red wire for power. Sometimes I'll use different colors for plus and minus power, but yeah, I've been using red wires for power and black wires for ground to try to keep things clear. You see, this is where the negative power is distributed from the power supply into that bottom red power bus. And then it's a little awkward, but this long red wire is where the positive voltage is distributed from the power supply up to that top red bus. And then I'm using this little thing with the minus sign is a ground. So this black wire is basically distributing ground to the blue power bar on the bottom. And then scope channel 3 I'm not using for this exercise. Scope channel 1, the yellow channel, is looking at the op-amp output. Scope channel 2, the cyan or blue channel on the display, is looking at the waveform output. So here this blue wire is from the waveform generator. So the waveform generator and scope channel 2 are on the left hand side of this 1K resistor, and then on the right hand side of this 1K resistor is op-amp, the op-amp inverting input, which is pin 2 on the op-amp package. Yeah, so there's a lot going on at pin 2 here, right? We have the right hand side of the resistor, we have the two feedback diodes. Okay, so then let's take a look at the output waveforms and the input waveform a little more carefully. Okay, so you can see I'm triggering on the waveform input, so that's scope channel 2. So it's always a negative signal, so my trigger level is down here at minus 2 volts. And then the yellow scope channel is the output of the op-amp. And then let's see, so if we look, we can look at the voltage. So the different voltage scales for channel 1 and channel 2. So the input waveform from the waveform generator is a triangle wave going back and forth between minus 4 volts and 0. So there's minus 4, 0, minus 4. Okay, so here's like 0, minus 4, 0, minus 4. And it's always negative. And remember we said that if the input signal was negative, we expect a positive output signal. So here the output signal is always positive. Here's 0 volts going up to 1 volt. So the output signal is going back and forth between 3 or 4/10 of a volt and 6 or 7/10 of a volt. You remember when an ordinary diode is fully on, its voltage is, you know, between 6 and 7/10 of a volt. We call it a diode drop. So that kind of makes sense. For the part where it's most on, we get about 0.65 volts here. And then because of that logarithmic, you know, as the argument gets bigger and bigger, the slope of the logarithm function gets smaller. So this is this flat portion here. And again, we call this the barn roof distortion. So it kind of looks like a barn roof or a gambrel style roof. And then down here, where the input signal is small in magnitude, the slope is quite big of the logarithm function. So, and again, this is kind of like the sides of that barn roof. So like the top of the barn roof, the sides of the barn roof. So, so here you can see that I guess a relatively small change in current corresponds to a pretty big change in voltage across the diode for this section down here where it's just barely turning on, right? So we're kind of like 0.3, 0.4, 0.5, 0.6 volts across the diode. Now, I think the next thing we want to look at is what happens if we shift the input signal a little bit. Let me just look at my notes on that. Okay, let's try removing the DC offset in the waveform generator here. So here, let me get myself out of the way, and we'll go over to wave gen, and we can remove this offset, and then we'll go back over to the scope. Oh, and I think we want to remove the offset on the scope channel. Oh, first of all, let's trigger consistently. So we'll move this scope trigger level to 0. And then let's get rid of the offset on this, and let's put it on a scale where it's readable. Oh, that's pretty decent. Okay. So how do we make sense of this? So it seems like if the input signal is 0, or close to 0, then there is, input signal is 0, there's no current through the diode, so there's no voltage drop across the diode, so the output is basically 0. So we see 0 output when we have 0 input. That kind of makes sense. Then, as we start to flow a little bit of current, once the diode kind of starts to turn on, so you know that there's that like pretty steep functional form of the diode curve. Actually, let me just draw that. I'll draw it kind of qualitatively. So our diode current versus voltage curve sort of looks like what? Yeah. So here's the diode current versus the voltage across the diode, and you know, so it should be, it's 0 back here. We only have one diode, it's 0 back here, and then it turns on pretty quickly. So, and then this is this is our diode drop region, right? So this is like maybe 6 to 7 tenths of a volt. So you know, once the diode starts to turn on, then you should be in this steep region, like in the 0.6, 0.7 tenths of a volt region. So I think that sort of makes sense, because see, once we get any significant current through the diode, now we're up kind of getting close to the 6 tenths of a volt range. But then once the diode is on, the current increases the voltage increases very slowly as the current gets bigger. So it's relatively flat here. You can see that the biggest magnitude of the output is where they have the biggest magnitude of the input. But the output, the voltage across the diode changes very slowly as a function of the, as the input to the diode changes. Okay, so, and then on the other side we just have the same thing mirror image, because that's why we have the second diode. In fact, if I just go and pull out one of the two diodes, here, let me do that. That's always kind of fun. So, let me just rip out one of the two diodes. So I don't know which one I'm looking at, so I'm going to take here, let me try to do it so you can see it. I'll take one of the two diodes here and just pull it out. Okay, and then you see that basically half of that curve has disappeared. So now we get the response for the negative side, but we don't get the response for the positive side. I think it looks a little funny because I think the op-amp goes a little bit nuts because there's the feedback path, the negative feedback path is broken once the voltage flips sign. So I think that's why we see something that looks a little bit funny down here. But anyway, you can see we basically, yeah, actually what's happening when the output wants to be positive, there's no feedback anymore. So then it just goes, I think it just slams all the way to the limits of the power supply. In fact, here I'm kind of making this up as I go, but we could just take a look at that. So let's Let's try 2 volts per division here. Yeah, so you see it just gets stuck pretty close to the 9-volt power supply. Here, let me get this window out of your way. So here's 9 volts. So the 741 can't go quite all the way to the power supply rail, but you can see it's like about 8.5 volts, and then it doesn't want to go any further. So when the feedback is broken because there's no current through the disconnected diode, then the output just saturates at the power supply limit. Okay, so that's why that end looks a little funny. All right. So anyway, I think the neat thing about this circuit is that again, you can make an output which is proportional to the logarithm of the input. And so then we know how to make an adder, and we know how to take a logarithm. So now you could, and then I guess you could take an, how would you take an anti-logarithm? I guess if you put the diode here instead of here, you could take an anti-logarithm. So if you have logarithms and then addition and then anti-logarithms, you could imagine making a multiplication circuit. So that's kind of a fun potential application. So the op in op-amp, operational amplifier, really is intended to mean that you can do mathematical operations, because, you know, addition, subtraction, you can multiply by a constant very easily. You can do logarithms, and then you know, you can imagine putting some of these things together and doing like multiplication or division. So this is the end of the second of 2 labs where we're basically showing you pretty much straightforward applications of the golden rules of op-amps. And the next lab after this departs a little bit from that nice picture, in that we will see some of the real-life non-idealities of op-amps. Seeing the non-idealities of op-amps is kind of irksome, and people kind of find it a little hard to follow. But it's important to be aware that there are limitations to the behavior of op-amps. They're not perfect, because when you want to choose an op-amp for your particular application, you want to choose an op-amp whose limitations are not going to, you know, qualitatively affect the performance of the circuit you're trying to build. So it's good to be aware of the limitations of op-amps so you kind of know how to work around them if you are stuck with a particular op-amp, or how to choose an op-amp that minimizes those issues for your application. So that's the next thing we'll discuss with op-amps is these real-life limitations of op-amps.